Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper, Charlie to friends, and I'm a theoretical physicist currently working in the University of Helsinki in the Helsinki Institute of Physics as a university researcher. And I'm a cosmologist, which means I study the universe, the contents of the universe, how things evolve, how things interact, cool things happening inside the universe. And I remembered to turn off my keyboard just before the cat walked on it this week. Yeah, so I'm a cosmologist, I study the universe, and I love chatting to people about all of the cool things I get to study. I realized I messed up my introduction today. I'm a cosmologist, that means I study what the universe is made of, everything going on inside the universe. I love being a cosmologist, and I love chatting to everybody about all of the cool things that happen in the universe. For anyone who doesn't yet know, Cup of Cosmology is an interactive stream. The idea here is that you people can ask me anything you want about cosmology, about space, about astrophysics, about physics in general, or about academia, about the two lovely cats I have to either side of me. You can ask me anything you want, and I will do my best to try to answer your questions. As always, I will not have all the answers, but we can try to figure out the answers to some of the questions as we go. So this stream relies on you all asking questions and me answering, which means you have to jump in the chat, say things, say hello, tell me where you're coming from, ask me questions, and of course, do all of the usual YouTube stuff. There's buttons you can press, there's a subscribe button, there's a like button, there's some comments you can leave. You know what? You know all of the usual buttons you can press, make stuff happen. If you're watching on Twitch, there's also buttons you can press. I'm just less familiar with those buttons, but press buttons, make stuff happen. It's basically what being a scientist is, looking at something and saying, what happens if I do this? Oh, whoops, that was a bad idea. I just don't press the close tab page. You don't want to close the stream. So, as you might notice, my introduction was all over the place today. My mind's been kind of scattered today, but I'm ready to talk to everyone about science. I see we have a bunch of regulars coming in. As always, if you're a regular, welcome back. If you're a first-time viewer, welcome. It is great to have you all here. Let's see, who do we have? We have some of the regulars coming in. Oh, just stuff happened when I moved my mouse here. Okay, yes, we have Ben, Ange, Paul. Great to see you all. Paul, I know you missed it last week. I know I missed 4 months. Great to have you back today. Scott, Praf, great to see all of you. David Howden, glad you got my message and realized that I'm back. We have Taz, we have Lothargo, lots of the regulars here. Very, very cool to have so many regulars coming in. Pressing unfamiliar buttons is the best. Yeah, so press a button, see what happens. You know, if you ever walk into a room and there's a big red button, you should absolutely press it. Even if it's do not touch, that means you should absolutely press it. For legal reasons, please don't quote me on that. But do press all of the buttons, especially big red buttons. They're always very fun ones to press. Anyone else find the intro music very relaxing? Well, I'm glad you find the introduction music very relaxing. The introduction music to Cup of Cosmology, the one that plays the waiting music, was actually a piece that was commissioned specifically for a Cup of Cosmology. It is actually the music that plays during the trailer. Cup of Cosmology has a trailer. It's on the YouTube channel, and it's just welcome to Cup of Cosmology. It's a 1.5 minute long, or 96-second long trailer that I made. I taught myself video editing just to make the trailer. If you haven't seen it, please go watch it. I put a lot of work into it. And I commissioned an artist by the name Swift Beats to make the music for my trailer. And now I just reuse that music as my waiting music because it's the right length to kind of get my settings and get people coming in. So the music you hear is the music from the trailer. It's a commissioned piece by Swift Beats, and it was made specifically for the trailer. So if you go watch the trailer, you'll see that the music actually really aligns with the trailer. Okay, comment from Prath. I learned a new Finnish word recently. There are many new Finnish words. I keep learning new ones. I'm not sure if I'm retaining all of the ones I'm learning. Finnish is a fun language. Finnish is a very difficult language. Basically, just add a bunch of Ks and you've probably got a Finnish word. And then make 16 versions of it depending on its position in the sentence. That's basically how Finnish works. I love learning Finnish. I'm working on it. It's just a language I'm struggling with, but I'm slowly getting there with the Finnish. Looking for the button label, start vacuum, DK, do not press. I mean, would a complete reboot of the universe be a terrible idea at this point? Probably we shouldn't reboot the whole universe. That's probably not a good idea. So if you see a button saying start vacuum DK, maybe don't press it. Although for science, it would be fun, for science. Okay. I see there is a question from Angie of what are your thoughts on the new planned mission to the moon? Which one? Has there been a new one announced? I'm not sure if there has been a new one announced, but I very much believe in space exploration. Okay, yes. So, Pras, you learned the Finnish word kalsarikanit, which means to be drunk in underwear. Yes, that is a Finnish word. Indeed, I agree with that. So, my opinion on space exploration is it is very good to do space exploration. It is very good to go to the moon. It's a shame we haven't been there in quite a few years. It is scientifically very, very interesting. It is also, it's space, the final frontier. Of course, we have to go. We have to be out there voyaging in space. However, there are a lot of things that we need to be aware of when doing such space voyages. And there are a lot of ethical considerations which people like NASA, ESA, the various space agencies across the world have done a lot of work into, put a lot of work into figuring things out. So space missions that are done by space agencies, I think, are very good because they have a strong foundation of, we've been doing this for years, we've figured things out. We talked about things like what we can and can't bring along with us. Basic example that I can give of just like thinking about this, if you take anything to the moon, regardless of what it is going to affect the natural system there. If you bring something that is not part of the moon to the moon, you are affecting the system. For an example, if you have tardigrades, little space bears on your satellites or on your mission, and it crashes into the moon's surface for whatever reason, you have now brought a life form to the moon which shouldn't be there. So these are things that are ethical considerations that we need to be aware of when doing space missions. And this is why I'm very skeptical of private companies doing space missions, because the correct safety and ethical guidelines are not followed. For an example, was there literally anything gained from a billionaire shooting a car to space? Absolutely not. Should that have happened? Absolutely not. But it did, and here we are. So my thought on upcoming space missions is yes, caveat if done properly. Now, the upcoming one specifically that is being talked about is Artemis 2, which is NASA's plan. Thank you for reminding me of the names here. I was just like, which space mission? Yes, Artemis 2. Now, Artemis 2 is going to do a flight around the moon. It's not going to land on it, but it's going to do a flight around. It's going to be a crewed mission. It's going to go around the moon and come back. And this is something that will be very interesting. We haven't been to the moon in a long time. Even if the astronauts don't set foot on the moon, it is still very, very interesting to see that we can actually get astronauts as far as the moon, kind of do a round trip and come back. This is something that is a very good thing to do. Scientifically very interesting, much more worthwhile than letting billionaires do a loop around space and then call themselves astronauts, looking at some very specific pop star. But yes, a NASA-approved mission to slingshot around the moon and come back to Earth is a very good idea. It is a good next step. We haven't been to the moon in a while. It's good to check that we still have the technology, or that our current technology can get astronauts to the moon and back, even without a landing. So my thoughts on the upcoming moon mission is very, very cool. It's good that we're now having a crewed mission to the moon again, even if the astronauts don't go down. It's just scientifically a very necessary thing. And it's good that we're getting back into these kind of ideas. However, if you were to ask my opinion on a certain billionaire trying to colonize Mars, I would have a much more negative out view on that, because space exploration is something that belongs to everyone, and it is something that I believe should continue to be operated by space agencies and not by individuals who have their own invested interest. And just as a warning to y'all, I'm in a mood this week. I've already picked like 2 fights. So if you want me to rant about billionaires, that is a topic I will happily rant about. And this week I seem apparently very prone to picking fights. They're all very valid fights to pick, and I have no regrets about them, and I will always call men out on their bullshit. But also, yes, if you want me to rant about anything, today is the day to get me to rant about things. But yes, I see there's some other questions here, but let's stick with the moon one a minute, and then we can go back to the other questions. There's some questions about vacuum decay and cosmological constant. But just sticking to where we are, there was some comment here from Paul: when we go extinct, the tardigrades we brought to the moon will evolve into the leading species in the solar system. That is a possibility. Like that is the thing. Like, what happens to the species that we accidentally took to the moon? And that wasn't just a random example. We have accidentally left tardigrades on the moon. This is something that did happen. So yeah, there is now a species there that shouldn't be there. It's not native to the planet. We've already seen on Earth what happens when we bring species to different countries. It is a bad idea. When we try to bring a species to another planet, it's just not going to be a good idea in general. Okay, sticking on this topic, and then we'll go through other questions. Comment from David Howden here. I suspect many people will question whether government agencies are an infallible source of ethics. That is a very good thing to question, and I would argue absolutely not. Governments are going to be political. Governments are going to make mistakes, especially in some countries. Governments are always an infallible source. This is a thing. But the good thing of space agencies is that they're less political than the government that funds them, hopefully. Of course, because of where the money goes, it's going to be politicized. Science does not exist in a vacuum, even though science deals with facts and observations and theories and maths and things that should be objective. The people doing science are humans and they are subjective. Science will never be apolitical because science does not exist in a vacuum. Therefore, can we trust our governments to have valuable space agencies? Probably not completely, but the good thing is that space agencies like NASA or ESA have been around for a long time and have already got a strong body of knowledge to draw upon. So when I say that NASA has kind of figured out the ethics of space travel, that doesn't mean it's infallible, but it means that they have a strong background of trying to make this work in a good way. They have a bunch of experts trying to make this work in a good way. They are at least aware of these issues. So while they will not be perfect, no space agency is perfect. And the clearest example of this is the way that space missions are named. For an example, this is something that is very divisive, very political. Space agencies are not infallible. The governments behind them are not infallible, but it is at least slightly more reliable than billionaires playing at space exploration. So while I agree that governments are not infallible, I do believe that government agencies like NASA, like the European Space Agency, are the ones that should be leading the way in terms of space exploration. Okay, sticking with this because there's still many questions about this. I know there's other questions to come back to. Hey, Nina, great to see you here as always. Very nice for you to pop in. Okay, so sticking with the idea of moon exploration, other questions we want to go back to later on. We have already sent astronauts around the moon and brought them back. We lost that skill. We are learning it again. Exactly. This is something we have done in the past. It is something that was very useful in the past. And now we are repeating this. This is not completely new science, but it is something we haven't done in quite a few years. It is new in the sense that we need to remind ourselves how to do it because we have done it before. We know it can be done. But now there's the question of, can we do it now? And this is a very good step to take. As Ange points out here, a very big difference between actual space exploration and billionaires playing at space, indeed. Okay, sticking with this, I see there's a question there about a black hole. We're going to get to that in a minute. So, sticking with these topics here, the tardigrades on the moon are like the start of the Adrian Tchaikovsky book, Children of Time. Yes, indeed. Here's my cat. Yeah, cat, come back to jump up on the table. Yes, so yes, we took tardigrades to the moon. The moon now has a life form that shouldn't be there, and we still haven't figured out how to deal with this fact. And yeah, you can write many sci-fi stories that start along these exact lines. Okay, very good question to start with space exploration. I'm all in favor of space exploration, caveat when done properly. Another reminder that we should all be watching For All Mankind. I have been told that. Yes, I've been told that many times, and it is on my must-watch list. I believe it's only on Apple TV, and I have too many streaming services as it is. The whole point of streaming services is it was supposed to replace cable, where you needed to have like 15 different channels that you paid for, and now we just have to pay for 15 different streaming services. Yeah, but For All of Mankind is on my watch list. As soon as I acquire it, I will watch it. But also these days I'm distracted by, rewatching Bridgerton because that does not require any thought. And that currently is a good thing to watch. Okay, so going back to the top, there were some other questions I wanted to answer. Space exploration was a great topic to get us started today. It is a topic that is very much fitting for my mood of let's rant about stuff. But moving on, there was another question that I saw from Paul that I wanted to answer. Where was it? Yes. Question from Paul asked a while ago. Do you think we can learn anything from the fine-tuning of cosmological constants, or just coincidence, or maybe someday we'll find out it had to be those values? This is an excellent question. This is a very, very good question. So I think we can take a minute to talk here about what we mean by fine-tuning and cosmological constants and things like that. So when we do science, there are different types of numbers. There are some that we predict, and there are some that we measure. Now, the ones that we predict are usually ones that you pull out of your formulas, of your equations, of your predictions, and there are other ones that we measure. Sometimes we measure numbers that are completely random, and sometimes we measure numbers that seem too good to be completely random. And we can think about a couple different numbers I'm just going to pull out here. When we talk about gravity, gravity is the force that is responsible for keeping planets in orbit around the sun. It's responsible for making my trusty pen fall down. Fun fact, I checked, this is 6 inches. Going back to last week where I was like, by eye, this is 6 inches. It's just shy of 6 inches. So my guess was actually correct. Anyway, gravity. I drop pen falls down to the floor. Apparently that was less stylish than it should have been. Pen falls down, planets stay in orbit. Now, when we calculate the gravitational attraction between bodies, we need to know the mass of the two objects, the distance between them, and the gravitational constant. The gravitational constant is a number, 6.7 times 10 to the something in some units, doesn't matter exactly what number it is. This is a number that we have scientifically measured. This is a number that is going to be constant every time we measure the gravitational attraction between two bodies. You are going to have this gravitational constant there. This is something that our theories tell us there should be a number. We do a bunch of experiments. We measure this number, 6.7 times something in whatever units. Okay, so we have a gravitational constant. This could have been anything. There's nothing special about this number, but it's a number we have measured. We have measured it time and time again. We are very sure that this is the number, and this is the number that we use to calculate the gravitational attraction. Then there's other numbers that seem a bit too good to be true. And this is where we enter what we call the fine-tuning regime. Now, I'm going to give one example, and that is when we measure the curvature of the universe. Is it slightly less than 6 inches when accelerating due to gravity? No, when accelerating due to gravity, it's going to change because time changes when objects accelerate, if they accelerate almost to the speed of light. Me dropping the pen does not make it move fast enough to change its size. You can't use that as an argument for things moving this slowly. If I threw it at the speed of light, then its size would change. So I want to talk about the curvature of the universe. And to do that, I need to bring up my trusty image, because you'll know what I'm going to bring up. So as soon as Restream figures out what I'm doing here, Restream is just buffering. Okay, this image here, cosmic microwave background radiation. This is the oldest light we have in the universe. This is a snapshot of what the universe looked like almost 14 billion years ago. This is the afterglow of the Big Bang itself, the first light in the universe. So, the cat walking across my screen again. Okay. So, this is the cosmic microwave background radiation. It is behind everything else in the universe. It is leftover radiation. It is redshifted to be in the microwave range of the electromagnetic spectrum. Cosmic microwave background radiation. What is this light? Glad you asked. Y'all don't know this. You've never seen this image before. In the early universe, there were 3 main components. There were protons, electrons, and photons, which are particles of light. The universe was very dense, very hot, very messy. These 3 particles were constantly interacting. No light could travel through the universe because it was too busy bumping into the other things. As the universe cooled down, protons and electrons combined together to form the first atoms. This meant that the photons were free to break away and travel throughout the universe. They have been traveling, these photons, these particles of light, have been traveling freely ever since, and today they make up the cosmic microwave background radiation. By looking at things like the cosmic microwave background radiation, by looking at how hot and cold the photons are, the particles of light, that is what is shown with the red and blue here, by looking at how many hot ones and how many cold ones there are, we can actually figure out a lot of things like what is the universe made of. We know that the universe has about 25% dark matter, about 5% normal matter, about 69-70% dark energy. We know this from the cosmic microwave background radiation. None of these numbers seem special. 5% normal matter, sure. 65%, 70% dark energy, sure. It's a number. It could be any number. These are the numbers we've measured. Something else that we can measure from the cosmic microwave background radiation is the curvature of the universe. So I want to talk about the curvature of the universe a minute, because we are used to curved surfaces. You know, our planet is a sphere. This is something we know. My table is flat. This is curvature. This is something we can agree on. Now, measuring the curvature of the universe is actually quite difficult, because you can't really pick it up and look at it from every angle and say, like, okay, yeah, this is what it looks like. This is the surface. This is the curvature. But what we can do is ask the question of, how do objects move in the universe when we remove any other presence? So if I have a curved surface, let's say I have a ball. I have a ball that just happens to look like a CMB. So I have a ball. This is a curved surface. If I try to balance anything on the top, it is quite likely to roll down, right? Because there is curvature. It is very difficult to balance anything on a curved surface because there is curvature. Now, this pen is moving because of the curvature here. Of course, it's being pulled down by gravity. My analogy doesn't completely hold, but we know that in the universe, if space-time is curved, this is what we interpret as gravity. So the curvature of space-time is going to cause motion. If the space-time is moved, if space-time is curved, objects moving through space-time will experience this curvature. They'll move in a different way. So when we talk about curvature of the universe, what we're basically saying is, if I put a ball somewhere in the universe, away from all the other gravitational forces, away from planets, away from stars, away from galaxies, in a void, I just put a ball there. Is it going to stay still, or is it going to move? If it stays still, the universe is flat. The curvature of the universe is flat. If it moves in any way, there is curvature in the universe. Now, there is different types of curvature. You can have positive or negative curvature, depending if it looks like a ball or if it looks like a saddle or a Pringle, you know, those chips that are wavy in different ways. So the curvature is measured with one number, which we call the curvature number. This number could have been literally anything. You could go from any negative value to any positive value. You could have negative curvature, you could have positive curvature. Now, the curvature that I am coming back to the constants and the fine-tuning, getting there. Now, the curvature that we have measured in the universe is curvature 0. Curvature 0, which means the universe is flat. So this is something we've measured in the cosmic microwave background radiation. It's something we've also measured elsewhere. So the question is, why is the universe flat? Now, we can come up with a lot of theories, a lot of models that explain why it's flat. But then there's the question of this curvature could have taken any number from minus infinity to plus infinity, and it happens to be 0, which is the only value that gives you a flat universe. Is this a coincidence? Is it by design, by some theory, by some model? And then we get into the question of fine-tuning. So has this number been fine-tuned in order to give us a flat universe? This is one example of fine-tuning. Then it gets more complex when we think about different models. Different models in cosmology, you know, we have our standard model of cosmology, which tells us the universe has this amount of dark matter, this amount of dark energy, and so on. These are models. And some of our models have numbers that may or may not require fine-tuning. For an example, if I say, I want to come up with a theory that involves space dragons. Okay, I want my universe to have space dragons. Now, I'm going to make a prediction and say there are 20 space dragons, because if there are any more, the space dragons would heat up the cosmic microwave background radiation, if there's any, and we would see them. If there were any less, they wouldn't account for the dark matter. I'm saying dark matter is made of space dragons. So I'm now going to make a prediction, or I'm going to make a theory where dark matter is made of space dragons, and I say, in order for this to work, the universe has to have 20 space dragons. Now there's a question of, is this a prediction? Potentially. But then if I'm changing it specifically to like this theory, this model, my space dragons, only works if there is exactly 20 dragons, that is fine-tuning. That number 20, there's no inherent reason why there should be 20 space dragons instead of 21, 22. So if I'm saying this model works, but only if we have exactly 20 space dragons, I am fine-tuning my model. So this is just to give the context here of what we mean by fine-tuning and what we mean by things that are measured. There was a follow-up question when I was talking about the gravitational constant. Where was that? I scrolled, I lost it. There was the question when I was talking about the gravitational constant by David Howden. Is it slightly, not that one, sorry, that was, yes. Question from Prath there. Is G proved to be constant everywhere? Not completely everywhere when I'm talking about the gravitational constant. We're not 100% sure if it is exactly the same in every situation in the universe, but approximately. And for the sake of this example, we're going to say yes. So bringing it back, the question that I was answering, the question that Paul asked is, do you think we can learn anything from the fine-tuning of cosmological constants, or just coincidence, or maybe someday we'll find out it had to be those values? I'm not completely sure. I think the more you fine-tune your model, the harder it is to theoretically justify this. Like, if I say we need 20 dragons for my model of dark matter to work, why 20? But then let's imagine I say I need 20 dragons who breathe fire once a day and who have red hair for random reasons, because otherwise, I don't know, you'd see the reflection on something. I'm not saying the universe is made of space dragons here. This is just the example. The more constraints I add on my model, the more I'm fine-tuning it. So does this actually give me any useful information? Potentially. It tells me the scenario in which space dragons work. But now let's imagine that I actually find space dragons and I find exactly 20 of them, and I find that they produce fire once a day and that they have red hair. So my red-haired, sporadically fire-breathing dragons, and the exact 20 of them do exist. Let's say I find them. So now it's a question of, was my fine-tuning correct? Is it a coincidence that there's exactly the right amount to work? Or do we have that amount because otherwise it wouldn't work? And this is where we get into the debate. So becomes a bit of a philosophical debate at this point. There is fine-tuning in cosmology. Some of our models have numbers that seem suspicious. Like, why was it this? Why not any other number? And an argument you can make is, if it was any other number, we wouldn't be having this debate. We're having this debate because it is exactly this number. So yes, I think this was just to give you an idea of what is meant here by fine-tuning. So the question of, do you think we can learn anything from fine-tuning? I think we can learn about model building. We can learn about how things work. But there's always going to be a question of why these numbers. And the more fine-tuned your model is, the more numbers you add into it that have to be these numbers, the harder it is to theoretically justify. At this point, I need to justify why we have exactly 20 fire-breathing dragons with red hair in order to explain dark matter. And then it might be that someone else comes along and says, well, I can explain dark matter without any fine-tuning. It's a massive thing that interacts with gravity but doesn't interact with light. This requires less fine-tuning than the space dragons. So maybe you're more likely to choose the model that doesn't involve as much fine-tuning, because the more fine-tuning you do, the harder it is to theoretically justify. So I hope that makes sense. That was just a very long answer there to just explain this whole idea of fine-tuning in cosmology and what we mean by fine-tuning. You can take the argument further and ask, why do we happen to live in a universe that can support life? Because maybe if you change the mass of the proton, or you change the mass of any other particle, maybe you would no longer support life in the universe. So some people will then say that cosmology, or our models, are fine-tuned around the assumption of humans being here. But also, if you don't have that, if you're in a universe where humans couldn't exist, where life couldn't exist, then we wouldn't be having this conversation. So I think that's an excellent question that you asked there, Paul, about fine-tuning in cosmology. I know I went on a roundabout way to answer here, but the basic idea is, some numbers are predicted, some numbers are measured, and some numbers are predicted to be very, very close value because else it doesn't work. And then it's a question of how precise, at which point are we kind of over predicting. I agree with David Howden. We should always choose the model that maximizes the amount of space dragons, because who doesn't like space dragons? Next stream, if I remember, I'm going to wear my little dragon necklace. I have a very cute dragon necklace. The dragon has a name. Her name is Amy. I'm going to wear my cute dragon necklace at some point, because then when I talk about space dragons, I can be like, I have one. It's not a space dragon, but hey, I'm a space physicist and I'm wearing a dragon, therefore it's a space dragon. I don't know what happened at some point, why space dragons became my go-to model when making up like crazy scenarios. It's always space dragons. It has been for about 6 years now. And I do not remember the origin, like what started it, but it's always been space dragons. If you watch enough of my streams, space dragons will appear at some point. Pondering that necklaces have names. Of course necklaces have names. Why wouldn't a necklace have a name? If you're going to wear it frequently, why wouldn't it have a name? Yeah, so the reply to that is a very no spicy thing to do. Who gives necklaces a name? Necklaces should have names. Everything should have names. All of my electronics have names, because then if they ever take over, they at least know that I was kind enough to give them a name. So, you know, the day printers take over, or the day electronics take over with ATM machines leading the charge, I will be ready, because all of my machines have names. Hey, David Dunn, great to see you over on Twitch. Thank you for joining. You joined in a very coherent part of this conversation where we're talking about electronics taking over the world and why you should give your necklaces names. Okay, so I think we covered the fine-tuning one. I know I got lost in some details there, but I don't think there were any follow-up questions to that. There was a question from David Howden about the curvature. Would a universe with different curvature be a different size? It would not, and that is a great question. So the curvature and the size are not directly related. Of course, the amount of curvature tells you how closed or open the universe is, but the universe is still infinite. The universe is infinitely big. Everything in existence is part of the universe. There's nothing outside of the universe. The size of the universe, therefore, is the size of everything in existence. We can't define an edge to this. So it becomes a bit trippy when you start thinking about it, because if I'm saying, you know, the universe is closed, it's a sphere has a size, but no, the universe doesn't have a size. This is why curvature of the universe is always a very difficult thing to visualize. But yes, it's a very difficult thing to visualize, but curvature is a great example when we're talking about fine-tuning, because of any possible value, it happens to be 0. Okay, now let's go back to the top, because this was, I think I've answered 2 or 3 questions, but there were other questions I wanted to get back to. Okay, so that was a great question there from Paul about fine-tuning of cosmological constants. Very good question. Okay, moving on. There was something else that I saw that I wanted to answer to but I haven't gotten to yet. That was how that sentence was supposed to go. I saw there was a comment from Taz at some point of like, press this button to initiate proton decay. Please don't press that button unless you want the universe to end, in which case, please go ahead and press that button. Okay, there was a question from James about gravitational waves. It's a very cool question. Question from James. If gravitational waves carry gravity, which is what we discussed last week at length, if gravitational waves carry gravity, do they attract with each other? Will 2 gravitational waves interact if they pass by each other? Yes, absolutely. Gravitational waves do interfere with each other. So if you have gravitational waves from multiple sources and they overlap, they can interfere with each other. You get the interference of gravitational waves. However, this would be a very, very, very small effect. So gravitational waves are already kind of small, and we're talking about a very, very tiny effect on top of a very tiny effect. So while technically, yes, gravitational waves can interact with each other and with other matter, it is not an important enough effect to be the main thing we need to concern ourselves about. But for an example, if a gravitational wave, if two black holes smash together, more realistic, they produce gravitational waves. These gravitational waves are traveling throughout the universe. If these gravitational waves happen to encounter, for an example, a black hole, they will be affected by the gravity of the black hole. So gravitational waves can interact with each other, they can be distorted, and they can be affected or influenced by anything else with mass that they encounter along the way. In the same way that other waves will interact with each other, so do gravitational waves. So yes, they carry gravity, but they will attract each other. Then you get into the question of like, what is, if we're talking about a gravitational force associated with a gravitational wave, what is the mass of the gravitational wave? Because if we're talking about gravity, we need mass. And then it gets tricky, because at this point, we're trying to apply gravity to something tiny like a quantum system. It gets messy. But the idea is, yes, gravitational waves carry gravity, and therefore they also interact with each other. Now, that's a very cool question. Let me just catch up with the latest comments and then we scroll back up. We also discussed that gravitational waves can reflect, refract, and Doppler shift. Exactly. So, as gravitational waves are traveling throughout the universe, they can interfere with other objects. They can be redshifted. They can be reflected off of surfaces. They can be refracted off of surfaces. They can be moved around. And by surfaces here, we mean anything with mass. Don't know what they would reflect off of, though. What would they reflect off of? I'm not really... What could they reflect off of? That is a very good point. What would a gravitational wave reflect off of? I'm not exactly sure what they could reflect off of, but they can be distorted by any other object. And they can experience Doppler shift. Doppler shift is the very cool thing that waves get kind of stretched or compressed as they're traveling towards you or away from you. If this is a wave that's moving through the universe, when it's coming towards me, I'll see it being slightly squashed. When it's traveling away from me, I'll see it being slightly stretched. This is something that you can test directly with sound waves. If you have an ambulance that's coming towards you, you can always tell by the sound the ambulance is making whether it's coming towards you or moving further away from you, because the sound will slightly change. The sound wave, when it's traveling towards you, gets more compressed. When it's traveling away from you, it stretches out a bit. So basically, this is the Doppler shift. The waves moving... Oh, my slinky got stuck again. It is the waves moving as they get closer or further away from you. Gravitational waves can also experience Doppler shift. And they do experience this. So a gravitational wave traveling towards us is going to be slightly more condensed than a gravitational wave traveling away from us. This is a very cool thing. Gravitational waves behave like any other wave in that regard. They can be stretched, they can be compressed, they can be interfered with, they can refract or diffract off different surfaces, and they will experience Doppler shift. So yes, gravitational waves do everything a normal wave would do, except it's made of gravity instead of something like light or water or sound. Okay, I just saw a quick question before we jump back to the questions I was answering. Question from David Dunn of how are the cats? They're both doing very well, thank you. They're both on this cat tree next to me, asleep. They've had a very hyper day with a lot of... Well, they spent the morning asleep in the sun, and then they spent the afternoon zooming about. So they've had a great day, I think. And of course, like 10 minutes before I started the stream, they started zooming around. But now they've both settled into bed. So yes, the cats are doing very well. Thank you for asking me. I'm always happy to talk about my cats. There was a funny story, funny tangent, and then I'll get back to physics. Last week, I was at a fancy event, kind of like a super fancy dinner for friends who just finished their PhD. So I was at this super fancy dinner, and there was a photographer, and I was kind of aware that there was a photographer, but ignoring the photographer. So I was chatting to people, chatting to my friends, and obviously at some point in the evening, I was like, does anyone want to see cat pictures? And I pulled out my phone and I started showing pictures of my cats. Because of course, what else am I going to do at a fancy dinner? I'm going to pull out my phone and show pictures of my cats. All of the people around me were very happy to see photos of my cats. But this week we got the photos of the event, the official photos from the photographer of the event. And I was looking through them, and it just happened that almost all of the pictures that feature me, I'm showing a cat picture on my phone. Like, have you seen my cats? Can I interest you in my cats? So based on these pictures, I very much came across as a crazy cat person, which is not inaccurate. But most of the photos from this formal event feature my phone with a cat picture on, like, have you seen my boys? So yes, apparently I show cat pictures more than I realized. Well, the photographer just happened to catch me in those 5 minutes when I was showing that. I don't think I had my phone out all evening with cat pictures. I usually don't have my phone out at these events. But apparently the photographer captured me being very much like, cats? So their names are Otto and Kutte. Otto is the older one, Kutte is the younger, dumber one. Not that either of them is that smart, I'm just getting glared at for calling them a dumb boy, which is not helping because he looks very dumb when I do that, when he does that. So yes, two cats, Otto, Kutte. I've had them just over a year now, they are rescues. Otto is 10, Kutte is 8, we think. We're not completely sure how old they are, but we think they're 10 and 8. Okay, Comment from James here. Gravitational waves are your new brain-boggling subject for downtime thinking. Yeah, me too, actually. Although I'm not sure if it counts as downtime thinking for me because that is my job to think about gravitational waves. But the good thing is I can just be like sprawled out on the sofa thinking about gravitational waves and be like, yeah, I'm working. I'm paid to think about this stuff. I'm paid to think about gravitational waves, and that's very cool because there's memes about that are a productive day for a physicist is I thought about a lot of stuff. I wrote some of it down, but I thought about a lot of stuff, and that is actually pretty accurate. We do think about a lot of stuff, and that also means that I can just be chilling with my cats thinking about gravitational waves and be like, yeah, I'm working. Of course I am. My brain is working. So yes, I agree. Thinking about gravitational waves in your downtime is a great thing to do. Just not sure if it counts as downtime for me. Okay, back through the comments because there were a lot of questions. You had a lot of very good questions today, and I know I haven't got through all of them yet. So back to where we were. Gravitational waves carry gravity. That's the one we were talking about. We covered that one. Then we went on some conversations about billionaires, and I ranted. Then we had a very good question that I just need to remind myself of a topic before I answer it, but we can do this live because I do not exactly remember what a space elevator is. I know what space elevators are technically, but let me just check what a space elevator is because there was a question from Sen. As usual, if I don't know your names, I'm just picking out part of your username and using that as your name. If you don't like the part of your username that I'm choosing to use as your name, please introduce yourself in the comments. Those of you that I know, I will call by name. Otherwise, I'm just going to be like part of username, easiest part to pronounce. There was a question: can a space elevator remove mass from a rotating black hole? So this is why I needed to check that I was remembering correctly, because I'm not entirely sure how we'd relate a black hole to a space elevator. So the idea of a space elevator is kind of something that we would use to transport stuff from Earth to orbit using kind of a cable. So it would basically be like throwing stuff up to space in a controlled way with a cable. So the question was, can a space elevator remove mass from a rotating black hole? Now, this is an interesting question that I think I need to think about for a bit. I need to ponder this. Yes, I need to ponder this. I'm pondering. So, pondering with T. Okay, a black hole is a region of the universe that is so dense that nothing can escape, not even light. Once you've crossed the event horizon of a black hole, you are lost to us. You are gone forever. Do not randomly jump into a black hole. You will not have a fun time. Not that you'd actually feel it, but you would not have a fun time. But black holes are regions of the universe that are incredibly dense and that nothing can escape because of the huge gravitational force. In fact, you would need to be traveling faster than the speed of light in a vacuum in order to escape the gravitational pull of a black hole. As far as we know, nothing in the universe can travel faster than light in a vacuum, and therefore nothing would be able to escape the gravitational pull of a black hole. So this is the idea. Black holes, big, massive objects, nothing can escape because you'd need to be traveling faster than light in order to escape. So now the idea here of a space elevator. So a space elevator is this technological idea, a kind of piece of technology that would basically be an elevator to take things to space. Kind of massive thing that just lifts stuff up until it's approximately in orbit. So if you want to use a space elevator on a black hole, my first problem is where would you tether it to? Because black holes don't really have surfaces. Black holes are these regions that are extremely dense. They can either be formed by a star reaching the end of its lifetime and collapsing, or the early universe just being so dense that a region collapses to form a black hole directly. But that means there is not a clearly defined surface of a black hole. There is an event horizon. An event horizon is the region. Oh, I just realized I can use my plushie. 1 sec. Ah, that's the wrong way. Just messing up my light section. My lights there. Okay, I forgot that I have my black hole, white hole plushie. Black hole with its accretion disk, white hole, hypothetical, not sure if they exist. Let's ignore the white hole for now and focus on the black hole. So we have a black hole, region of the universe that is so dense that nothing can escape. Around a black hole, we usually have an accretion disk. This is matter that is gradually falling into the black hole, getting closer and closer and being eaten up by the black hole. This part here, the kind of surface of my plushie is actually the event horizon. That is the point of no return. Before you reach the event horizon or the surface of a black hole, you can still turn around. You could still escape the gravitational pull. Once you cross this event horizon, you are inside the black hole. And at that point, the gravitational pull is too intense for you to turn back or for anything to come out. This is why it looks black, because not even light can escape. The event horizon of a black hole is not a physical surface. It's not a point that you could crash into. It's a point where the gravitational force becomes so strong that you can't escape. Which actually means if you jump into a black hole, you will never notice the point at which you cross the event horizon. It's not like you hit a physical barrier. Nothing essentially changes except the gravitational pull gets substantially stronger. So this means that we don't really have a clearly defined surface of a black hole. So my first problem with a space elevator on a black hole is where do you put it? Because you can't attach it to the surface. Then there's also the issue of all of the tidal effects where the gravitational force as an object gets closer is going to feel, as my trusty pen, gets closer to the black hole, is going to feel a stronger gravitational force at the tip than at the bottom of the pen, which means the tip, this pen is basically going to experience a technical term of spaghettification. It's going to be stretched and eventually torn apart because the gravitational force on the tip ends is a lot bigger than on the bottom of the pen. I'm saying the tip of the pen and the bottom, and I'm confused because then when I write, that's the top. Okay, the clicky part of the pen and the top of the pen. What are words today? So the clicky part of the pen is the back of the pen is going to experience less gravitational force than the front of the pen, so it's going to be torn apart. So issue number one, you can't attach your space elevator to a black hole because there's no surface. Issue number two, if you were trying to attach it, say you had it somewhere, it would be torn apart. It would not be stable because of the tidal forces or the different forces on the clicky part of your space elevator and the tip of your space elevator. Another issue is that even if somehow you manage to get your space elevator somewhere usable close to a black hole, you would not be able to you would not be able to remove anything from the black hole because the amount of energy you would need to remove something from a black hole and make it travel faster than the speed of light is an amount of energy that is impossible to achieve in the universe. It's not that you could throw an infinite amount of energy at it and it would work. It is impossible to accelerate objects to the speed of light, no matter how much energy you pour into the system. So even if you poured in a huge amount of energy to pull apart your black hole, it would never be enough to pull it apart faster than the speed of light. And therefore, you would never be able to pull matter out of a black hole. So I love this idea. It's a very cool thought experiment of, okay, we have a device that's purpose is to shoot things up from the surface of a planet to orbit. Could we do that on a black hole? At least three issues why we couldn't do it. The first one is you don't have a surface to anchor it to. The second one is your technology would get ripped apart. The third one being even if you overcome these hurdles, you still cannot overcome the gravitational pull of the black hole. And so you would never be able to pull matter away from the black hole. Cats are now activated again. You would never be able to pull matter away from the black hole because it would require an infinite amount of energy, and we do not have an infinite amount of energy. So cannot be tethered, would be destroyed, not energetic enough. Conclusion is you cannot use a space elevator to pull matter out of a black hole. But I love this thought experiment. I love these type of ideas of here's a piece of technology that we're working on. We don't yet have space elevators. They're still theoretical, still hypothetical, sorry, but they are something that people are working on in the same way as, we're working on teleportation, several years away at least, but technically it could be potentially possible. Okay, so space elevator on a black hole, very cool concept. Probably wouldn't work, but cool idea, cool thoughts. And also it gave me an excuse to get out my plushie. Thank you. I love this plushie, white hole, black hole plushie. It is very good as a fidget toy because you can just play about with it. Not my best fidget toy, but it is a good fidget toy sometimes. Okay, very cool question. Love that question. That was a very interesting thought experiment. So thank you for that question. I know it was asked quite a while ago, but we got there eventually. Okay. Coming back to the comments and the questions here, there was the comment from Prath when I was saying that my job, I get paid to think about physics, saying in that case, I'm already an excellent unqualified astrophysicist. Yeah. If you know, obviously it's not what I do all day, but at least a part of my workday is thinking stuff up. If I come up with a new theory, then I successfully thought stuff up. Often we don't come up with new theories, we just come up with new ways of solving our problems. But that means that I can be just staring into space saying, like, yeah, I'm pondering the secrets of the universe, and be like, oh shit, I'm paid to do this. Right, that's true. I am, in fact, paid to ponder the secrets of the universe. That is such a fun thing. I remember during my undergrad, that was an ongoing joke of like, did you think about a lot of stuff today? I was like, yeah, I thought about a lot of stuff. Did you think about a lot of stuff? Yeah, we thought about a lot of stuff. We're on the path to becoming excellent physicists. We thought about a lot of stuff. Which is basically it's basically what all scientists do, right? Like we think about stuff. This is why my one of the professors who's been the most influential. One of the professors, I'm laughing at myself because I'm on such a like ADHD train of thought of like, here's 50 different things you didn't ask that we're going to talk about in one breath. And I keep forgetting to finish my tea because brain is spiraling. So I'm aware of what I'm doing. I'm laughing at myself and I'm not stopping. Let me drink my tea. Okay, tea is done. Now, what I was going to say, one of the most influential teachers I had was my philosophy teacher when I was 17 and 18. Really, really good teacher, really good at teaching us philosophy. We had philosophy and then history of philosophy. And he made the comment during one of the first lessons that modern day philosophers are just physicists because there were a lot of parallels. I don't agree completely. There is nuance. There are different fields that focus on different things. But a lot of the like well-known historical philosophers did have their own views of the universe. They had their own ideas. You know, we've heard of the Platonic solids and the ethos and the ether. Sorry, these were these were things that were kind of early models of the universe. Cosmogony, they used to call it, early models of the universe, and they were previously done by philosophers. Point being, I went on a tangent. My philosophy professor was great. I really appreciate him. He's one of the reasons I ended up getting into physics. And point being, thinking stuff up is something that a lot of scientists do, a lot of philosophers do, and it's something that there's a lot of overlap in those fields. But yes, point is, I get paid to think stuff up, and that is a very cool job. Bringing it back from, I would say a tangent, but it was more like, here's a random thing that just happened. Okay, back to the questions. Physics equals philosophy plus maths. Yeah, but also philosophy does have a lot of maths. Like if you take a course on metaphysics, where you combine philosophy and physics, that is so cool. Then you get into fun things like logic, and yeah, then it gets really cool. So you might go on a tangent of what is a chair and does any four-legged object count as a chair. If you see me looking that way distracted, it's because the cats both have zoomies right now, and there's a lot of activity happening off screen. Okay, we were talking about these topics. Very, very vague thing. We were talking about topics. Comment from Prathia, even on neutron stars, the tallest mountains are 5 centimeters or so. Even neutronium isn't strong enough to make a space elevator on a neutron star. Exactly. It's very hard to have mountains on neutron stars. So neutron stars are a type of star that is very, very dense, but doesn't have enough gravity to be a black hole. So it's a quasi black hole, an almost black hole that didn't quite make it. But they are dense enough to fuse protons and electrons together to form neutrons, which is why they're entirely made of neutrons, and we call them neutron stars. Actually, a logical name for once. But neutron stars barely have mountains on the surface or ridges because the gravitational pull kind of makes things spherical. So you couldn't even build a space elevator on a neutron star successfully because of the gravitational pull. So building a space elevator on a black hole is not going to be feasible. Okay, there were some comments because I mentioned last week we talked about gravitational waves carrying gravity. And there are some comments here from Paul and James, like, I need to go watch last week because gravitational waves carry gravity changes your understanding. Yes, so when we know that the universe has 4 forces, right? There's the Electromagnetic force, which is electricity and magnetism. This is one we're used to. I turn on a light, there's boom, light, let there be light. I can put a magnet on the fridge. Electromagnetism, pretty well understood. There's the weak nuclear force, which is responsible for radioactive decay of particles. There's a strong nuclear force, which is responsible for holding things together inside protons and holding atoms together. And then we have gravity. Gravity is the force responsible for planets staying in orbit around stars, for pens falling down when I drop them, for black holes, for all of these cool things. Now, we know how some of these forces are carried. Usually, for three of them, the first three that I mentioned, there is a particle that carries that force. Electromagnetism is carried by photons, particles of light. If you have any electric or magnetic interaction, what you are doing is you are exchanging particles of light or photons. If you have any weak interaction, you have two bosons, which are just a type of particle, which are called the W and the Z boson. These are the ones that if you have any weak interaction, these appear. For the strong interaction, we have gluons, another type of subatomic particle. Gluons glue things together, excellent name. They are a particle that glue things together. Gravity, on the other hand, is difficult to discuss because ideally, we would also want a particle that carries a gravitational force, right? If we have particles for all the other forces, we would like a particle that carries a gravitational force. However, we do not yet know which particle, if any, carries a gravitational force because that would require having a good understanding of how gravity works on the quantum level, because when we move down to particles, we're talking about quantum stuff. We do not know how gravity works on small scale, on tiny subatomic scales. Gravity is a force that describes long distances across the universe, black holes, planets, all of this. When you try to use gravity on the quantum level, it becomes very, very difficult. We do not know what happens on the quantum level when it comes to gravity. In order to do this, we would need a theory of quantum gravity, and this is something we just don't have right now. But we are pretty sure that gravitational waves are kind of distortions of gravity. So a gravitational wave is carrying a gravitational effect, in a sense. When we have two black holes spiraling around each other and crashing together, this is going to produce gravitational waves. So if we think about the fabric of let's think about the universe as if it's a trampoline or a big sheet. You put an object with mass there, it's going to distort. You're going to get the curvature of space-time. This curvature of space-time is what tells objects how to move. This is the basic idea of general relativity. I know there are other questions here to answer, but there were people curious about this, and I don't always assume that you watch every stream. So this is just a reminder. We talked about this last week. So, yes. Einstein's general relativity, or the theory, our best theory of gravity currently, basically says that objects with mass tell space-time how to bend, and the bending of space-time tells objects how to move. So anything traveling in the universe is going to experience, anything with mass in the universe, or anything in the universe, is going to feel the curvature of space-time. Object with mass curves space-time. Curving the space-time tells objects how to move. They follow the curvature. Going back to our conversation earlier of the curvature of the universe. So a gravitational wave is a ripple in this space-time. And if you look at it, what is a wave? It's a series of peaks and troughs, or troughs, however they're pronounced, peaks and valleys, because I hate the word trough, trough, because I never know the correct pronunciation for it. So imagine this is my gravitational wave. It has peaks, it has valleys, it is traveling throughout the universe. But what is it a wave of? It is a wave of space-time, which means it is curvature of space-time. It is a distortion of space-time. So a gravitational wave is essentially a gravitational distortion. So when I say that gravitational waves carry the gravitational force, what I'm saying is they are carrying gravitational information. The information they carry is gravity. So therefore, they are carrying the gravitational force. Now, we do need to add the caveat here that there is still the uncertainty of, is there a particle that carries this? One possible answer to that, if we want to get into possible ideas of quantum gravity or in that direction, would be a particle known as the graviton. The graviton is as the name would imply, the particle that would carry the gravitational wave. A question we aren't yet able to answer is, are gravitational waves made up of gravitons? This is one idea. If we assume, electromagnetic waves are photons, are gravitational waves gravitons? We have not yet confirmed if gravitons are real or not. Currently, it is one of the ideas we have to try to unite the gravitational force and the quantum physics, the language of quantum mechanics. So, when I say that gravitational waves carry gravity, we are not saying that a gravitational wave is the equivalent of a photon which carries the electromagnetic radiation, the electromagnetic force. What I'm saying is a gravitational wave is a distortion of space-time. Gravity is also a distortion of space-time. So a gravitational wave carries a distortion of space-time. Therefore, it carries gravity, but not in the same way that a photon will carry the electromagnetic force. So I'm just adding some nuance here because I think it's important to make this distinction of it is not exactly the same as a particle carrying a force, but it is basically a propagation of gravity, which a gravitational wave is carrying gravity, in a sense. So this is something I talked about last week. I'm not sure if it was clearer or phrased differently last week, but because there were people in the chat here confused when I mentioned this, just thought I'd summarize what we discussed last week. If that doesn't make sense, as always, do let me know in the comments. These are hardcore topics. I don't expect you all to suddenly understand quantum gravity. I don't understand quantum gravity. Nobody understands quantum gravity. Gravitational waves are a very complex topic, and the questions you are all asking about gravitational waves are very advanced questions. I love that you're asking very advanced questions, but also do not feel bad if you don't understand the answers to these questions. Let me know, because then I can try explaining it differently or finding other examples or other ways of discussing it. But if you're baffled by gravitational waves, don't worry. So are physicists. We're also baffled. Physicists baffled. So, yes, gravitational waves are really, really cool. Gravitational waves are distortions of space-time, and in a way, it is a way of moving gravity. Nice to see you, David Dunn. Thank you for dropping by. Always lovely to see you here. You should all go follow David Dunn also on Twitch, because he does some astronomy streams as well. Comment here from Paul. Seems like philosophy. Does a tidal wave carry water, or does water cause a tidal wave? Indeed. Does a gravitational wave carry gravity, or does gravitational wave does gravity cause gravitational waves? Yes, it is the same thing. Very cool topics, very, very cool questions, but very, very hard to kind of wrap our minds around that this is, we think, how gravity works. But very cool questions. Okay. There's a comment here. I need to wake up early in gym. See you crazy people approximately. Yeah. Thank you for popping by, guys. Enjoy your gym. I have a lot of respect for people who get up early to go to the gym. Good for you. Have fun. Enjoy your workout. I will not be getting up early to go to the gym. Also, mainly because I'm apparently completely incapable of going to bed early. So at least I should not get up early as well, because my sleep schedule is already messed up enough as it is. Okay. Comment from James. You come here to be baffled. It is the allure. That is good. It's like, come here and be baffled by the universe. We can be baffled together. Scientists baffled. Yes. I mean, that is literally the point of space, of science, right? That is literally the point of science, is looking at something and saying, I don't know how that works. Let me go poke it with a stick to see if I can figure it out. That is what we do. We don't know something, so we try to figure it out. That is the point of science. Looking at something and going like, what's that? I don't know what that is. Let me go figure it out. And that is what makes science so much fun, so much more fun, because it is trying to figure out things that are baffling. And I honestly think that it is, like, figuring things out in science is fun, but finding something new that nobody knows the answer to and being like, everyone's baffled by this, that is great fun, because then you're like, well, let's all be baffled by this together. And yeah, what is more baffling than gravitational waves? But a lot of things, but especially gravitational waves. Okay, I think there was some question that I missed at some point, so I'm just going to scroll back to the top of the comments. I didn't mean to go that far up. I'm going to scroll back through the comments. As always, if I do not answer a question, I am not deliberately ignoring you. They just sometimes get lost, and I sometimes forget to forget to answer them or don't see them. So if I ignore your question, please feel free to ask again, and I will try to answer if you ask again. Where were we? I can't even remember the question I was answering, but we went on a tangent because James asked about if gravitational waves carry gravity. Then I answered a different question. Then we came back to that one. Like we talked about space elevator and then came back to gravity. Okay. There was a question from Ben. What do you think about advances to the theoretical Alcubierre drive? That is something I never know how to pronounce. So I don't think we're going to go into that topic too much today. Briefly, an Alcubierre, however you want to pronounce it, that is a name I will never pronounce. The Alcubierre drive is a hypothetical warp drive idea. So it's basically a way of achieving faster than light travel by contracting space in front of you. So instead of traveling faster than light, you make the distance you're traveling smaller. You kind of move space-time around you. It is something that is hypothetical. So the question of what do you think about the advances to the theoretical drive? I'm not sure what advances. Have there been advances? Is there something new? I have not heard of any advances to this. I'm also currently not going to jump into exactly how a warp drive works, but the basic idea of a warp drive is you warp space-time. So instead of having space-time being kind of this flat sheet, you compress space-time in front of you and stretch space-time behind you. So then it gives the illusion, or then you can kind of travel more distance in a shorter time, and you can achieve faster than light travel because you've condensed space-time. So basically, imagine I'm saying, I want to travel across this notebook. I want to go from here to here. So instead of traveling this full distance, what if I just kind of condense this, kind of like this? So now I can easily get to the other side because the other side is closer. That's the basic idea of a warp drive. How does that actually work in practice is something that I would need to recheck my general relativity lecture notes, and that's not something I'm going to be able to answer on the spot. So warp drives are a very cool idea for science fiction. They are not something we are anywhere close to building or developing yet. As to advances in the drive, I haven't heard of any advances. I also haven't been keeping my eye on that. So maybe if you do have some advances in that direction, Ben, let me know. Or if you've read some, if you personally have advances, or if you've read that, send me a link so I can look into it more. But currently, it's not ringing any bells in my mind that there have been advances to this topic. Other than warp drives are something that is fun for sci-fi, probably not realistic anytime soon. I'm just staying with your comments before I jump to the new ones to see if there's any other questions I missed, because I think there were some questions I missed, right? There was a question from Scott. I'm doing quick fire questions now. There was a question from Scott. At what mass does gravity kick in if not at the quantum level? No idea. To answer that, we would need quantum gravity. Any object with mass will produce gravity. If we go down to a particle has mass, does it produce gravity? Technically, yes. What does that look like? No idea. Quantum gravity. So yes, technically there is no specific mass at which gravity kicks in. Gravity should work for any mass down to the Planck mass, which is the smallest mass we can consider. So, smallest mass we can consider, but as to at which point it stops being quantum and starts being something we can describe from gravity, that is not a clear-cut distinction. Just at some point, it becomes hard to put these two together. Okay, there's at least two more questions I want to answer. One about JWST, one about CMB, one about pulsar timing array. Okay, there's at least three more questions to answer. Scott, I think that was your question that I just answered. Potentially, if not, feel free to ask it again. Don't poke a space dragon with a stick, you'll get burned. Yes, that feels like good life advice in general. Don't poke a dragon with a stick. Hello, cats. Why am I being stared at with the... Oh no, he's just getting comfy in bed. Okay. Yes, I don't know what the context was for don't poke at a space dragon with a stick, but yes, good life advice. Oh, but yes, because I'm saying there's something I don't understand. Let me go poke it with a stick. Maybe don't go poke your space dragons with a stick. Yes. Okay. Sticking on the topic of anything with mass causes gravity. Question from Paul here, very difficult question. A photon has no mass but can have lots of energy. Does it cause gravity? No. Technically, no. In principle, quantum gravity. I don't know. That's going to be my default answer. Like, I don't know. Ask me when we figured out quantum gravity. I don't know. But, we talk about gravity being produced with objects with mass, not objects with energy. Now, then there is the caveat that how do we define mass, and thus do photons have rest mass? Okay, photons, particles of light, massless. Do they produce gravity? Probably not. Maybe, I don't know. Ask me when we solve quantum gravity. Great question. Let me think about that and get back to you when we solve quantum gravity. Okay, back up to the top. Where were we? There were three other questions I wanted to answer. And we're going to try to do quick answers to these, and I've lost the questions. Were they really that far back in the chat? Okay, let's see. Let's just go through it again. Yes, there was a question here from John some time ago, almost an hour ago by now. I'm slow with the questions today because we keep going on tangents. Question from John. What is currently the best explanation for the high redshift galaxies JWST found that were heavier than expected? Has it changed much from when they were first discovered? Excellent question. I'm going to put a pin in that question because it's highly likely that in a couple of weeks I do a stream where we discuss these galaxies specifically. So I will put a pin in that. The kind of brief answer is that JWST, an ongoing space mission, has found some galaxies that are a bit heavier than we expected. This affects our models of galaxy evolution, but we're still trying to figure out exactly what this means. That is the short version, but I might be doing a stream about these topics very soon. So stay tuned, I guess. Okay, quick fire questions. Because there's a CMB question I need to answer. There's a pulsar timing array question I need to answer, and I'm just finding another 3 questions I hadn't answered. Question from Prath: did the universe have an epoch where muons and tauons were stable? No. So muons and tauons are types of particles that decay, so they're not long-lived. Basically, a lot of particles have like 3 families that we call them, or 3 flavors. The heavier one is more unstable, and they can gradually decay into other states. Muons and taus are particles, and tauons are particles that decay into lighter things. Have they ever been stable? I don't believe so. No. Quick fire answers here because it's approaching. We only have like 10 minutes to go, and there's still some questions to get through because you all have very good questions today. Okay. So we discussed those. We discussed the curvature. Then there was a question from John about the CMB, and 2 questions from John, actually. Let me answer the second one first. Second question from John, asked 45 minutes ago: have there been any updates to the variable dark energy finding DESI found hints of last year? Yes, see last week's stream. So recap, DESI, Dark Energy Spectroscopic Instrument, is a ground-based mission looking for dark energy. It is trying to map galaxies in the universe, so it is taking pictures of galaxies. It has already mapped over 6 million galaxies. By mapping galaxies, we get an idea of how matter is distributed in the universe. The further out into the universe we look, the further back in time we're looking. If we construct very detailed maps of galaxies, we can see how galaxies look today versus how they looked years ago when they're further away. So we can use this information to model how the distribution of matter has changed over time, which allows us to measure what dark energy is doing in the standard model of cosmology. So just to recap, universe has 3 main components: everything we see, everything we're used to, normal matter, 5%. We are a type of matter that interacts gravitationally but not electromagnetically, that's dark matter, 25%. Dark energy is the remaining 70%, which is this weird type of energy that is driving the accelerated expansion of the universe, and that's all we know about it. Now, in our standard model of cosmology, dark energy is constant in time. That means that it acts the same way today as it has done in the past. It is always a constant force or a constant energy. However, the dark energy spectroscopic instrument, DISI, found hints that actually dark energy might be changing over time. It might be thawing. You might have a different way of interacting with dark energy today than we did in the past. DISI had this first data release in 2024. It was very exciting. It was like time varying dark energy. Is this a thing? They put out another data release where they found that their results are solid. So it's still the same kind of thing. It's not sure enough to say it is preferred over our standard model of cosmology. It just fits the data slightly better. They got more data. This model still fits the data slightly better, not enough to completely overthrow our standard model of cosmology. I talked about it last week, but the short version is yes, there has been an update from DISI. The update is our data has not budged, basically, which is a good update because sometimes there are experiments will find something in a first data release and then they realize they had badly calibrated their instruments, or with more data it goes away. These are the blips, the things that disappear. This happens often. It is a natural part of the scientific process. So when DISI put out their second batch of data and they said actually it agrees with the first batch, this is good because it means they're kind of more convinced about what they're doing, what they're saying is more sound. So while the data didn't say yes to time varying dark energy or no to time varying dark energy, it said we believe our results more than we did a few years ago, more than we did in the first data release. I talked about it a bit more in depth last week, but that is the quick version of the update. Okay, other question from John, and then I'm going to finish scrolling down and then see the latest comments. I'm not seeing the newest comments just now because I'm stuck in the middle of the conversation. Other question from John, because oh wait, that was, how many questions are there? I thought there was a CMB question. There's still a CMB question. Where's the CMB question? Coming. What do you think of the idea of black hole stars in the early universe? If I understand right, these are black holes with accretion disks so dense that they undergo continuous fusion like a star. Yeah, that is a very cool idea. Did I talk about that last week as well? Huh. Okay, so a black hole star is a hypothetical idea where you could have a star that basically has a black hole at its core. So you can have a star where the core of the star is so dense it could collapse to form a black hole. So you'd still have the star going on around it, but you'd have a black hole at the center. This is something that, depending on the model, is more or less stable because you can hypothetically have fusion happening around a black hole, where you'd have your black hole here, you have your kind of accretion disk around it, but the accretion disk can also be a star, can be having fusion, where it's fusing hydrogen together to make helium in the same way, on heavier elements in the same way a star does. So I think black hole stars are a very cool idea. I don't think I can say much more on them right now. I would need to check some things. Okay, quick fire answers, just glancing through this. At some point there was a CMB question that disappeared. Where was my CMB question? I thought, there it is. Another. John, you have lots of questions today. That is very cool. There was another question, the CMB question. Okay. I'm going to answer that, then I'm going to jump to the bottom. Question from John, asked about half an hour ago. How does the CMB image scale to the modern expanded universe? I mean, if you take one of the smaller overdense regions in the CMB, what size structure would that region be in modern cosmos? Excellent, excellent question. So, excellent question. We have our CMB, have a beach ball with my CMB. I love this beach ball. Don't ask me where I got it from. Perfectly legally acquired beach ball. So how does this is the CMB, the cosmic microwave background radiation put on a sphere. So how does the CMB image scale to the modern expanded universe? So if we take one of these regions are usually like a fraction of a degree of the sky. So how does that scale to the modern universe? If you take one of the smaller regions, what size structure would that region be in modern cosmos? So that is the thing that then I'm wondering how to answer that question, because this is light that came from the furthest reaches of the universe. So it doesn't really need to be scaled up to today. Like when we take this and we say this patch here is 2 degrees, or a fraction of a degree, that's how much it occupies on the universe around us. So yeah, I'm not completely sure how to answer that. When we look at the CMB, it is the furthest thing away from us. and we have the kind of the angular size, the size of patches on the CMB. Now, because we have regions here that are overdense and underdense, where you have more matter and less matter, which somewhat corresponds to the regions where you have colder photons and hotter photons. These overdense regions are the same ones that then set the seeds for galaxies to form around them. So every overdense region in the early universe is more likely to correspond to a region with more galaxies today. But as to the scaling size, like when we talk about it in terms of degrees always and not in terms of cosmic scales. So we will say like these dots on the CMB, these photons are specific degrees. In fact, I might even have a figure to show this. Let me see if I have a figure. I do have a figure. It's a question of can I find said figure. You're going to get a plot now. Okay, we're gonna go to a plot here. I believe, I'm not sure. I believe it's going to be somewhere. I don't remember which slide number it is, so we're gonna have to figure this out as we go. So bear with me while we go through my slide deck. Here it says this one, number 7. Okay, perfect. So what you're seeing here, this plot here has temperature on one side and angular scale on another. Basically, this plot is showing you how many hot and cold photons are there at different patches in the sky. So the first ones on the left side is if we take 90-degree chunks of the sky. So basically we divide this sky into not many chunks. We have like a 90-degree chunk, which is going to be a whole big triangle up here. It's going to be 1/8 of the sphere. 1/8 of the sphere. What is the ratio of hot to cold? That is what the first dot shows you. And you can see this on the bottom axis, that it starts at 90 degrees and it goes 18 degrees, and somewhere you have 1 degree. This is getting smaller and smaller. So the further to the right you are on this image, the more fine-grained you are going, the more into the details you are going, whereas the further on the left, you are looking at the bigger clumps. And you can see we go down to like 0.5 degree. The last number there is going to be like a percentage of a degree. It's like 0.01 at the end. So this is what we talk about in the CMB. We don't really need to scale it up because we're always going to talk about how much of the sky does it occupy. We're not saying like that is 2 centimeters big. We're saying it occupies this fraction of the sky. So it already kind of gets scaled up by the way we talk about measurements, if that makes sense. That was a very technical way of answering the question, but it also gave me a chance to show you the plot. From this beautiful image we have on the sphere here, that is the plot we get out. So very cool question about the CMB there, a CMB question that I was not expecting. Very cool. So the question of how do the kind of regions scale up to today, we talk about it always in degrees. So we talk about it already as in which fraction of the sky does it occupy. Then there's a whole other process you can do of like, what would that correspond to if you put a galaxy of the same size? But that's not comparing similar things. If that makes sense. That was a very, very good question. I hope that answered your question, John. Do let me know if it didn't answer your question. And I think that is all of the older questions now. So let me just scroll down to the bottom because I think now we have answered a lot of them. Okay, yes, catching up again to the bottom here. Oh, did I miss lots of questions? Yes. Let's just go through the last comments here. John, if that didn't answer your questions, do let me know. I think I just answered 3 or 4 of your questions quick fire. Catching up with the comments again now because I think I've now answered most of the questions. Just did some quick fire answers there. So there was a comment from Scott at some point of black holes can theoretically be made of photons. They're called Kugelblitzes. Not sure how that works. Yes, hypothetically, we could have a black hole made of photons. What that means in practice is a bit weird because we don't know what black holes are made of. We don't know what is inside a black hole. We don't know what a black hole is made of. Asking what happens if a black hole is made of photons, we don't know. We do know that Kugelblitz is not like a. Well, I was going to go on a rant because some TV series like using the word Kugelblitz as we don't know what to do. Let's use Kugelblitz. Fine, yeah. But don't take any knowledge of Kugelblitzes from things like Umbrella Academy. That is not a Kugelblitz. Okay, more comments here. A black hole stars were also last week. Thank you for agreeing with that, Scott. I was like, I'm pretty sure I've talked about black hole stars. I just don't remember when. Also, there was a pulsar timing array question at some point, and I have lost the pulsar timing array question. Where was my pulsar timing array question? Okay, I've lost the pulsar timing array question, so feel free to ask that again because it got lost somewhere. Okay. Comment there from Scott that you learn from Deanna Troy. Fun fact: my name is actually from Deanna Troy from Star Trek, so I was actually named after the Star Trek character. So if you wonder why I'm kind of a geeky nerd who likes space, you can blame my parents for naming me after a Star Trek character. So yes, if you say you learn stuff from Deanna Troy, hey, that's my namesake. Very good thing to just maybe don't believe all of the science you see in Star Trek as a general life advice, but yes, I am named after Deanna Troy, in fact. So if you learned stuff from Deanna Troy, you learned it from my namesake. Yeah, Umbrella Academy is not, in fact, a documentary. Well, it is a documentary on why people need to go to therapy, because realistically, most of Umbrella Academy could have been solved if those kids went to therapy instead of, not doing that and having the most dysfunctional relationship of any family unit. Yes, send your gifted kids to therapy, especially if they're superheroes. Because, power, responsibility, all that, you know how that happens. Okay. Some comments here. Does anyone find it coincidental that my CMB beach ball appeared around the same time the Louvre heist happened? No comment. I do not think the Louvre had any CMB balls. They definitely don't anymore. If you open up my attic, you'll find 20 more of them. Interesting. No, I can confirm that this is the only CMB ball currently in my possession. This is the only CMB ball I currently have, to my knowledge. There are not another 20 of them hiding in the attic. If I had 20 CMB balls, they'd all be positioned behind me. I just have this one. No comment on whether it came from the Louvre. To my knowledge, the Louvre does not currently have any CMB balls. Okay. Right. So let me just glance here quickly. I think I answered all of it, except there was found the question. Of course, another question from John. Are you familiar with a study using pulsar timing arrays to map dark matter clustering inside the Milky Way? Inside the Milky Way, pulsar timing arrays. Huh. Yes. So pulsar timing array is a way of measuring gravitational waves, and it's really, really cool. Like, I also talked a bit last week about how we measure gravitational waves, but the basic idea is we need very big detectors in order to measure gravitational waves. And one very cool idea is using radio signals coming from pulsars, which are rapidly rotating neutron stars. Rapidly rotating neutron stars will produce radio signals. And if there is a gravitational wave going through the universe, it will affect the arrival time of the signal from these pulsars. So if you have a network of pulsars, you have an array of pulsars, you can look at the arrival time of the light or the radio signals coming from these pulsars. And if anything travels through the pulsars, their kind of distance is going to change slightly. So the arrival time of the radio signals is going to change slightly. This is something that is usually very consistent. There's not much that changes the arrival time of pulsars. So you use a network of these in the galaxy to kind of measure gravitational waves going between these different stars, which is a very cool concept. We basically turn stars into a gravitational wave detector. Very, very cool. And you can measure a lot of different things with this, including, for an example, the distribution of matter within the galaxy, which helps us understand things about dark matter. So there are ongoing studies trying to use pulsar timing array to measure dark matter, and I think that is very, very cool. Found the question. Okay. One final question that I'm going to answer here. I think I might have answered all the questions actually by now. I found the pulsar one. So, I vaguely keep track of them as I go. I'm like, there's a CMB question, there's a pulsar timing array. These are the ones we need to get back to. We'll get there eventually. Final question I'm going to answer because we have hit the 90-minute mark. Can galactic bars be predicted from the mass and rotation speed of the central black hole? I'm going to say no. So we know that galaxies have different possible shapes. Some have bars in the center, some don't. The amount of arms they have changes, whether it's a spiral galaxy or like a globular clump galaxy. That's not the technical term. I'm forgetting the technical term. Elliptical. whether it's an elliptical galaxy or spiral galaxy. That was the technical term. These are things that there is a lot of variety within the galaxies, and there's a lot of different things that cause this. It is not necessarily just based on the black hole at the center. Now, we know that every galaxy has a black hole at the center, a supermassive black hole. Now, the rotation and mass of the supermassive black hole at the center is going to somewhat affect the galaxy, but there's not, to my knowledge, there's not a direct relationship of if black hole looks like this, galaxy looks like that. There is a connection, but to my knowledge, there are other factors that influence it as well, but that is not something I'm an expert in. Okay, and by galactic bars, we just mean a region at the center. Let me just draw what I mean here. Where's my... Yeah, okay. I'm just badly drawing some galaxies here. This here that you see, this would be a normal spiral galaxy where it has two arms. This here would be a galaxy with bars, where before the arms start, you have this kind of central bar in the middle. You know, this would actually be much more like that. So this is a normal spiral galaxy without bars. This is a spiral galaxy with bars. So you just have this kind of straight bar at the middle of the galaxy first. That is what we mean by galactic bars. The black thing I've drawn here in the center represents a supermassive black hole at the center of the galaxy. So the question is, do these have any connection? We're not sure. Okay, after today's session, let's all meet up at the galactic bar. Absolutely, I feel like that might be a good idea. Okay, 92 minutes in. Time to wrap up. Do galaxies rotate in the same direction as their central supermassive black hole? Yes. Yes, they do. Short answer. Because the conservation of angular momentum, it would be very hard for them to rotate in different directions. So yes. Your cat wants to know if there are any treats in space. Probably. I'm sure cats would be able to find treats anywhere. You know, if we ever do go on space exploration beyond the moon, we should take cats with us, because what alien species is not going to fall in love with our cats? So they might not fall in love with humans, but we can be like, cats? It's definitely not a flurkin. Flurkin? It's definitely not a flurkin. Oh, I can't believe I made an MCU reference. Not a fan of MCU in general, but you know, the cat is cute. Okay. I never really finish answering the questions. No, because you keep asking more questions, which is great. I love how many questions you all ask. We've had so many fun topics today. You know, we started on space exploration. At some point, we were talking about space elevators and black holes. We've talked about gravity a lot. Again, gravity is a fun topic. You know, I've had multiple chances to show the CMB. We talked about fine-tuning. So many cool topics. Thank you, everyone, for all of the questions. It is really, really fun. I genuinely love coming here and chatting to you all about these cool topics. And as I say, you know, I don't know in advance what we're going to talk about. I turn up and like, I wonder where we're going today. And it's always an adventure. It's like, oh, we're going down the path of space elevators and warp drive. Sure, let's do that. It's great fun. I love the questions. I love that you all have so many very cool questions. So thank you, everyone, for joining, for asking questions, for interacting, for being here. It is always so fun. As you all know, I did kind of a long break. I'm just still getting back into Cup of Cosmology. We were live last week for the first time in 4 months, live today. And it is so good to be back. It is so good to be back talking to you all, having these conversations, asking these questions. It is just so much fun. It's always such a nice reminder of like, yeah, these are cool people asking me cool stuff. Really fun. So thank you, everyone, for being here. This has been super fun. I'm not 100% sure if there will be a Cup of Cosmology next weekend. I would like to do one. However, I also have plans. I may have plans every single day this week except tomorrow. Yes, no, I have plans tomorrow as well. Anyway, Sunday next week, I'm not completely sure if I will be online. I will know kind of by Saturday if I'm going to be online on Sunday. As usual, if you want to check if I'm online, subscribe to the channel, because then you can be notified 30 minutes before I go live. If you subscribe to the channel, click all of the bells to get all of the buttons to get notifications. There's a bell button. In any case, at the latest, Cup of Cosmology should be back on 22nd of February, so maybe not the 15th, definitely the 22nd. So 2 weeks from now, that will be the same time as always, which is 8 p.m. in Finland, 7 p.m. if you're in Central Europe, 1 p.m. if you're on the East Coast of the US, 10 a.m. if you're on the West Coast of the US. As always, there is a time zone converter on cupofcosmology.com where you can figure out when the next stream is going to be in your own time zone. There's also a bunch of stuff you can check out on cupofcosmology.com. There's highlights, there's feature requests, there's a bunch of things you can check out there. Feel free to navigate the webpage, but there is also the time zone converter. But if you want to be sure you catch my next live stream, just subscribe to the channel, turn on notifications, and then you should be able to catch me. So, and yes, just quick answer here that whatever was keeping me away is dealt with now. Yes, there was a variety of things that kept me away from Cup of Cosmology for the last few weeks, for the last few months. Nothing major, nothing dramatic, just a variety of things that meant that Cup of Cosmology got deprioritized. But we're back, we're up and running, and I'm motivated to keep this going. And I think my cats are ready for some treats. Okay, this has been super, super fun, everyone. As always, thank you so much for joining. It is really great fun to come and chat to you all. Always, always great fun. Cup of Cosmology should be back either next week, latest in 2 weeks. I hope to see you all there. And I hope in the meantime, you'll take care of each other and stay curious.